friends, let's talk a little bit about problem solving in two-dimensional motion. So what you see here drawn before you is a problem where there is a ball that rolls off the edge of a cliff, and that cliff is 10 meters high. And the question essentially asks us, how far from the edge of the cliff does the ball land? Now you see before you are two data tables for our x direction variables and our y direction variables, but let's back up and talk a little bit about where those variables came from. So recall that projectile motion describes two particular situations. The first is that there is an acceleration of gravity, meaning the only force acting on the object is the gravitational force, and therefore the object accelerates downwards according to gravity. Now the second parameter, as outlined by your book, is that there is an initial velocity in the horizontal or x direction. That means that the object is not just moving up and down, but it's also moving left to right. Another concept that your book described for projectile motion is the idea that acceleration in the x is 0. So we'll go ahead and write that down as our third note about projectile motion. Acceleration in the x direction is 0. And what that means for us is that there really is no need to differentiate between initial and final velocities in the horizontal direction because those velocities do not change. A zero acceleration in the x direction also helps us to derive our kinematic equations for two dimensions. So let's take a break from this problem for a moment and talk about what toolbox or what tools we use in order to solve these two-dimensional kinematic problems. So you see here, and I'll highlight that in blue, our kinematic equations for one dimension. Delta x equals VIT plus 1/2 AT squared, VF equals VI plus A delta T, and quantity VF squared equals quantity VI squared plus 2A delta x. Now from these equations, we get our two-dimensional kinematic equation toolbox in both the x and the y. So let's look at the y direction first. For the y direction kinematic equations, or the vertical axes for our kinematic equations, let's take all of our one-dimensional equations and let's rewrite them using the variable y and using the subscript y to indicate to us that we're talking about the y-axis. So our first equation, delta x equals VIT plus 1/2 AT squared, becomes delta y equals VYI, or velocity in the y direction initial, times delta t plus 1/2 acceleration in the y, or AY, times delta t squared. Our second equation becomes Vy final equals Vy initial plus acceleration in the y, delta t. And our third equation becomes Vy final squared equals Vy initial squared plus 2 acceleration in the y, delta y. And that should not feel too foreign because all we're doing is taking the same one-dimensional kinematic equations and adding some subscripts. Now things are a little different in the x direction. So if you look to the left for the x direction kinematic equations, remember that our two requirements for an object to be moving in projectile motion is that the object is in free fall and that the object has some initial horizontal velocity. The third note that we wrote down about projectile motion was that acceleration in the x is 0. Acceleration in the x is 0. And what that means for us is that the x velocity doesn't change. There's really no need for us to differentiate now between x initial and x final for velocity because they're the same value. So Vx initial equals Vx final, and therefore we don't even differentiate between initial and final. We just call it Vx. So let's go through the process that we did for the y direction equations, and let's do it for the x. So if we take our first delta x equation, delta x equals VIT plus 1/2 AT squared, and we rewrite that in terms of x, we would have delta x equals Vx delta t plus 1/2 AX delta t squared, but recall that AX is 0, so the entire second term becomes 0 in this equation. And we're left with delta x equals Vx delta t. Now in the second and third equations, because acceleration in the x is 0, we are left with equations that don't make sense once the acceleration term drops off. So here, we see we're left with Vx equals Vx. And that is not an equation that is particularly useful for us. In the third equation, we see we're left with Vx squared equals Vx squared. So again, that is not an equation that is useful. We can't actually plug anything in to either of these. So the only equation that we really have in the x direction for projectile motion is delta x equals Vx delta t. And so that is why the variables in our x direction data table above are just delta x, Vx, and t. Okay, so let's move forward with solving our problem. So we are solving for delta x. So let's put 2 question marks down for delta x, because the problem says how far from the edge of the cliff, horizontally implied, does the ball land? Now if you look at the initial velocity, it is completely horizontal. This is a ball moving horizontally off the edge of a cliff. All of the 5 meters per second, all of the initial velocity exists in the x direction and moves the ball from left to right. Our Vx, therefore, is the entire 5 meters per second. If you wanted to see this mathematically, we could use our trig functions and we could say that this is a velocity vector and the angle between the horizontal, right, the dotted line that I'm drawing here, and the velocity vector, the angle between those are 0. So from your homework, hopefully you recall that in order to find the Vx, or the horizontal leg of the right triangle, that the length of the leg adjacent to the angle is equal to the hypotenuse times cosine of theta. So if we were to write hypotenuse times cosine of theta, cosine being 0, you would see that it's just equal to 5, because cosine of 0 is 1. So for those of you that like to prove these things mathematically, that is how you would do it. And for the rest of us, we can just recognize that if an object is moving horizontally off the edge of the cliff, all of the velocity is horizontal. All of the velocity is horizontal. Now we don't know delta t, so right now we are stuck because we would write down our equation delta x equals Vx delta t, and we'd see that we don't have enough information to solve this problem. So our next step is to look at the y direction. We'd look at the y direction. So if all of the 5 meters per second of the velocity is horizontal, then that means none of it is vertical, and Vy initial is 0 meters per second. For those of you, again, that like to solve things mathematically, what you're really saying is that Vyi is equal to the hypotenuse times sine of theta. So we would have 5 meters per second times the sine of 0 degrees. The sine of 0 is 0, and therefore this entire quantity equals 0. But again, for the rest of us, we can say that all of the velocity is horizontal, so none of the velocity is vertical. We don't know Vy final, but we might not need it, so we'll just put 1 question mark there. Acceleration in the y is gravity, negative 10 meters per second squared. Delta y is 10 meters, but because I think I will make my 0 the top of the cliff, which I'm dotting in blue, that is my 0, which means that the ball moves downwards in the negative direction, and delta y is negative 10. And delta t I don't know. Now here is the key to solving 99% of all of our two-dimensional kinematic problems, and that is this. Delta t does not have a subscript for a particular reason, and that's because the delta t between the x and the y of one singular motion is the same. And what that means is you can imagine someone kicking a soccer ball in a parabolic motion down the field. Let's say that soccer ball goes 100 meters down the field. It was a really, really far kick. Well, the time that it takes the ball to rise in the air to its peak and then come down again and land on the field is the same amount of time that it takes the ball to move horizontally the 100 meters. So delta t is the same in both the y and the x. So most kinematic questions will ask you to find t in either the x or the y and plug it in the missing axes. So recall how we hit a wall when we were trying to solve for x. We said we don't know t. So we're looking now in the y direction and asking ourselves, is there a way that we can solve for time? So if we use our very first equation, delta y equals vy initial delta t plus 1/2 a delta t squared, we can plug in 0 for vyi. Remember, never plug in numbers except when something is 0. So if I plug in vyi, I would see that this whole first term goes to 0, and I'm left with delta y equals 1/2 ay delta t, or delta t is the square root of 2 times delta y divided by a. If I plug in numbers, delta t equals the square root of 2 times negative 10 meters divided by negative 10 meters per second squared. And if I plug that into my calculator, I would see that t is approximately 1.73 seconds. And pardon me for a moment while I just double check that calculation. All right, so t is actually about 1.4 seconds. So we found delta t for the y direction, and now we can plug that in the x direction because delta t is the same in both axes. So here I'm going to write in for delta t on my y variable table, it's 1.4 seconds. And here in the x, 1.4 seconds. And now I can come back to my delta x equation and I can say, well, delta x equals vxt, so that's going to be 5 meters per second times 1.4 seconds. And so our delta x for this problem is 7.07 meters. So the answer to this question of how far from the edge of the cliff does the ball land, the answer is 7.07 meters. So this process is the same process that you will go through for 90% of your kinematic problems. Always draw a picture, create your variable table, choose an equation, figure out what you're solving for. And some key things to remember is that number 1, in the x direction, acceleration is 0. So x velocity is constant. And the second thing to remember is that delta t is the same for both the x and the y.